recording. All right. So remember this one. I will ask in English sometime, maybe as a quiz. Okay. Maybe as a quiz, I'll ask in English. What is the constant that is used to boost the observation, to boost the weights of the misclassified observation versus deboost the correctly based observation, correctly identified observation? Is that a good question for you all? You think? Because this is the critical step. If you understand this, the problem is over. It's done. The rest of them are purely computation. Everybody? Yes? Good? Talk to me.
Yes,
correct, Joshali?
Yes.
Rakesh?
Yes.
So how about now repeat that. I want you to repeat this. Can you say, Rakesh, what I said? You take half of, I will repeat one more time. If you want, you can write it. I want you to say that back to me. Half of logarithm of odds. Correctly classified versus incorrectly classified odds. Half of logarithm of correctly classified versus incorrectly classified odds. That is the constant that is used to boost and deboost. I'm using a word deboost. Okay, I don't know about that, but I want to say the opposite word. I don't. There is no other word people talk. So I'm going to call it as to boost and deboost the incorrectly classified observation versus correctly classified observation. Okay. How we do the boosting is through an exponential function. Okay. Basically, we are, whatever we did logarithm, we are doing an unlogarithm, right? Opposite of that, right? Our logarithm we did before, and then we are making it a reverse of it. So basically, we are doing a some measure of odds is being used to get the boost and deboosted values, so that it becomes now the algorithm next step gives more weights to misclassified observation versus not less weight to the correctly classified, because it doesn't have to work hard on the correctly classified observation. The algorithm doesn't have to work hard, right? It has to work hard on the misclassified observations. Is that a good? So can you repeat, Gaushali, what I said? What is the strategy? What is the trick that we used there? In terms of, these guys take years to figure this out, believe me, but we are learning it because they helped us to learn these things, apply these things. So we know it in one sentence quickly. How do we boost? It's a very simple classification problem. There are methods that we have devised for other things, regression and so on. But for classification, simple two-class problem, boosting is done by what? Rakesh, go ahead. What is the constant we use to boost and deboost?
So the half of the log of odds correctly classified versus incorrectly classified.
That is the constant that is used to boost
and deboost incorrectly and correctly classified.
To boost the misclassified observation, deboost the correctly classified. That means you have to take the weights from the correctly classified, give it to misclassified. So that misclassified now gets, it's like, there are 5 children in the home, and then 2 of them are weaker, 3 of them are stronger. So you want to take some amount of attention from the strong kids to give more kids, the kids who need to grow better, right? That's the same thing. Okay, can you repeat, Gaushali, now? Go ahead.
Sir.
Go ahead. I didn't hear you.
I'll repeat later.
Oh, you repeat later. Okay, fine. Soumya. Rajan is very smart. He immediately wrote it down. I like it. Love it, man. Go ahead. Soumya.
So half of the logs of the correctly classified versus incorrectly classified are corrected through exponential logarithm.
No, exponential of the constant.
Okay.
Exponential of the constant, not log. So the constant is half of the log of correctly classified to the incorrectly classified. Okay, odds. That is the constant, and that constant is taken to the exponential to boost the weights of the misclassified observations, deboost e power minus, deboost the correctly classified observation. That is the process basically for computational purposes. Go ahead.
And then the algorithm works on the misclassified to boost.
Correct. Finish it. You are very already there. Very close. To boost the
Classified.
Okay, there are two parts to it. Okay, two parts to it. One is find the constant, and then use the constant to exponentiate it to boost the misclassified, and then deboost it. For not to deboost it, you do the exponential of minus something. But what is the constant? That is half of logarithm of odds. Odds is correctly classified versus incorrectly classified. Everybody is good? Two parts. So slowly take your time to talk about the constant and then how you apply it to boost and deboost. Okay, go ahead. You want to say it one more time, Sonia?
No, actually, I'm a little bit confused right now.
Okay. Okay. So let's say Rajan. Let Rajan say. Rajan is very good. He wrote it down. Okay.
Oh yeah, thank you. Thanks. I mean, I just wrote on something saying that it's to boost the classified and deboost the misclassified using the constant, which is half of log of classified, incorrectly predicted, odds, and even.
Correct. Right? You didn't say how the boosting is done. The constant is done. You explained mathematically also. Boosting is use the exponential function of the constant. Based on, because exponential is an increasing function. When you put a constant, it's first of all alpha is a positive quantity. Okay, so exponential of alpha is positive quantity means it increases. Exponential of minus the alpha means decreases. That's it. Okay. Do you think you can say that now, Gaishali? Asami, are you still confused?
A little bit actually.
Okay, two parts to it. One more time. Kaushali, write it down. Okay, two parts to it. We define a constant computationally, right? I'm explaining more words now. We define a constant at every step, a constant. The constant is half of logarithm of correctly classified versus incorrectly classified observation odds. Okay, got it now, right? That is the constant. That second part, that constant is used to boost and deboost the misclassified versus correctly classified observation. To boost it, we take exponential of that constant alpha at the step t. Deboost means exponential of minus alpha at the step t. Everybody is good?
To boost, you use the positive exponential, right?
Exponential positive number. Alpha is always will be positive. Okay, because of because it's related to the probabilities. The odds will be positive. Okay, but log odds will be minus infinity to plus infinity. Okay, let's go back to that one. It could be a little bit confusing. So the odds is probability ratios, right? The correctly classified versus incorrectly classified. The 1 minus epsilon t divided by epsilon t is that's what it means. Correctly classified versus incorrectly classified is the odds. Logarithm of odds can be negative. Okay, based on the ratio. What is the ratio here? But remember, if epsilon t is smaller than 1 minus epsilon t, that means you have done a good job, but some misclassifications are there. Less than, if it is less than 50% here, epsilon t is less than, if this is beautiful, if epsilon t means what? Correct? Epsilon t means an error. 1 minus epsilon t means not error, right? 1 minus epsilon, if as long as 1 minus epsilon t is above 0.5, very important statement. I'm going to tell you why I'm saying about 0.5. If it's above 0.5, this number is always going to be greater than 1. Agreed? And because of that, and I will tell you why the 0.5 matters. I will come to you. Because of that, this quantity is always going to be positive.
Yeah.
What is the meaning of, that is the condition in boosting. That is not condition in boosting. This is a condition for selecting weak learners. A weak learner is one which is little bit above, better than random assignment. Little bit, 0.51, 0.5001, like that. Doesn't matter. Because remember, there are lots of learners we are going to build, right? Each learner is a tree. Lots and lots of learners we are going to use it. Sammy, are you there? Lots and lots of learners we are going to use it. A learner is a tree. Please write it down. Learner means a tree. Decision tree. Small decision tree. So because of that push, that the success has to be little bit better than randomness, okay? It has to be little bit better than randomness. This quantity will always be positive. Because it is always be positive, here e power, the boosting is e power. Alpha is always going to be a bigger number, right? More than 1. Not only more than 1, it's if it is minus, this will go to smaller and smaller values. This will go to bigger and bigger. That's all I want to say. This is going to be a bigger number. It is giving a bigger weight. This is going to give you a smaller weight. That's all it happens. You might find out, what is this strange looking weights here also, right? So there is something going on here. That is because this will become, this part alone will become adjusted weights. But then we have to make it as a probability. So we divide it by normalizing the total value so that the whole thing will become probabilities. Everybody is good so far? That is the end of the story. Don't worry about boosting anymore. In order to get that understanding, I'm kind of spending time here. Actually, I don't spend time here. No. I used to think that it is very hard for people to understand. Do you think it's very hard for people to understand? Do you think it is hard, Rakesh? You could understand, right? You could understand, right? Gaushal, you are good, right? Now, anyway, you might be distracted. I agree with you. You might be distracted. What is this strange looking, symbols and so on? But think in English. Think in your language. What are the languages, right? That's why I come to you about languages. Okay, but I have to speak in English because that's commonly used. That's okay. You all know those meanings, but try to say it in words. That's what Rajan did, right? Rajan, it's not okay. It's not bad, right? This is define some weight, constant weight. Constant, don't say weight now, because weight is used somewhere else. Constant, at every step we are going to calculate some constant, because as the step changes, we are going to calculate new constant. But that constant is always positive. Because it's positive, why is it positive? We want each time when we find a new tree, it has to be better than random assignment. So it is more than 0.5. So this will always be positive, because if it is less than 0.5, it will become a negative number. Okay, remember that. So that is the reason why we say we want every tree we introduce should be better than randomness. And large collection of little bit smaller tree, but large collection of them will beat a huge, very strong, beautiful decision. However beautiful it is. That is the mathematics of it. Now, Gaushal, you are good now, right? You are good, right? Same statement I repeated so many times. You are good now, right? Swami, you are good now? Gaushal, are you okay now? Getting there. Okay. Try. Don't worry about anything. You're all great. I absolutely believe in that. This is nothing. Actually, it's true. High school students can learn this too. I mean, they may still question what is this D sub P, I, Z, T, all those, but just say it in words. Don't say it any other way. Okay. Don't look at it in symbols. Look at it, hear it, say it in English. This is the probabilities. Okay. These probabilities are boosted by this method. But when you do that, this becomes, some of this will not be 1. Probability should be equal to 1, right? Some of them will not be 1. To make it 1, we sum the probabilities and divide each of those probabilities. So that now the sum will become. That's it. Everybody's good now. So this is that, right? Now let's go and finish the computations, right? That's what our purpose is. So the computation is here.
Can you enlarge the screen so we can see?
Okay.
Yeah.
Is okay now?
Yeah. So
Okay.
looks good.
So, well, whatever that I did this line one way. Remember, we construct line by line, and then we combine these lines to create this kind of what should I say? Bent line, okay, bent curve. this becomes one single curve later on, but initially we put a line, basically line, that's it. And then we put another line here, and then finally we have exhausted here. So we go on this direction, this variable, and then we put a line here. And when we combine this part, this part, this part, then to the left of that is all positive, to the right of is all negative, then the problem is solved. Are you with me? That is the strategy here. Good? Everybody? Are you with me? Okay, let's see. I have to see your face. Is it good? The idea, strategy is good, approach is good, right, Shirley?
Yes.
A question, but there could be moments when the data could be too heterogeneous that it could be lying all over the plane. So in that case, the strategy might fail, correct?
It is a matter of how finely you are going to keep cutting the search area. So you are saying probably there is also a plus here, for example. Let's say.
Yes, correct.
Okay, but there will be such a fine cuts we can make. That point alone will fall into that cut. Can happen that way. If it is not that, then I can capture it on this angle. If not here, I can capture it this angle. Okay. If not here, I can capture it as the third variable, third dimension. Somewhere I will be able to capture that alone if you want.
Okay.
Right? So the point is, in fact, think about it. A circle can be found by this automated method, by this algorithm. Suppose the observations are in a circle, as you said, exactly like nonlinear. It can be, we can figure it out that you cut them out all slices, but in this case it will not be just slicing on one variable, it will be both variable, right? Like slanted on two variables. I keep on moving like this, to the left, to the right, to the left, right. Can you imagine that it will be a circle will be found? I will show you.
Possibly, yes.
Possibly, I want you to, I want to show it to you because I thought that was beautiful. Okay, suppose I have the observations are, let's say, for ease of drawing this, I'm going to make it a little bit to my convenience like this, right? The circle, so not necessarily circle, it could be anything like this or like this. Okay, let's say this is the observation. What is the worst case? Circle is the worst case, you think? Let's make it the worst case. So what I am saying is, you will find your first decision line will be like this, let's say. To the left of this is your points, to the right of that is, let's say, outside circle. We are talking about identifying observation in circle, outside circle, okay? Are you with me?
Yeah.
So to the left of this, we are saying is inside circle, to the right is, there is a lot of error here. These are all the errors, right? These are all the errors. If I say to the left is a target, to the right is the reference, okay? Understood now?
Yeah.
So now let's take this one, another, I will put another straight line. Right? To the left is this, to the right is this. To the left is target, to the right is reference, let's say that. So you can see that by an intelligent combination of various lines, I'll put actually the thousands of lines here, that will exactly bound this as a circle. Do you agree with me?
Yes.
But outside this was error before, but with this is not an error. This was not an error before, but with this it's an error. But by a intelligent combination of this, this collections of lines, I'll be able to target, and to find all these observations, distributed observations in the data set. Am I making sense to everybody? Now, is it okay, Swami? So Rajan, now you're okay. Fine.
Yeah.
So you can, however non-linear it is, we can find that out. And to see, that is the beauty of machine learning, right? They will cut it so fine. They will cut it so fine. Now you might wonder, is it possible that it is over predicting? That question is there, right? Is it possible that it will over predict? The beauty of this is called adaptive boosting because it is adapting itself to next step, Rakesh, right? Every step it is adapting based on the previous probabilities, right? It is adapting. The boosting method is called adaptive boosting. There are other types of boosting also available, but this was the first one that revolutionized the ideas. Okay, so the idea is, it turns out it is not over predicting. That's why it became very popular. It is not over predicting. Okay. So with that, let's go and finish the computation. Okay, let's finish the computation. I was trying to show you here. Yes, is that correct? Yeah, this is the one. But I was showing an Excel sheet. Is everybody is now watching this one? So we said this was the initial probability D1. Now I will connect it to D1, D2, alpha, everything. Epsilon. This is the initial probability. Every observation is assigned initially as 0.1, 0.1, 0.1, right? Initially. Okay. But then we found out that this line here alone, right? Let me draw that line also in perspective, so we keep it in perspective. This is the line based on x1 variable, right? This line alone is used to predict first step, right? So in this case, we are predicting the target now. Remember that. We are predicting targets are plus. Targets are plus. We are predicting targets are plus. And it correctly identified this one and this one. Correct? This correctly identified this one. This is what the 1, 2, 3 observations are ordered in that way. Okay. But it did not predict this. These things are error. So these are error. I quoted as number 1 and 0 to say they are error. Okay, I think I should do it as maybe better is error, right? Error is a better word. But it is one value. Let's keep that as a one value 1, right? Error. Oh, why am having, how do I stop? Okay. So this is error. This is error. Hey, come on. Okay. These are 3 things error, right? Everybody? Soumya? Are you there? Right?
Yeah, yes, sir.
That's error. Okay. Now, its probability is 0.1, but we want to boost this. Remember that? I'm boosting it. Eventually, it becomes 0.17. But I take the weights from here. Remember that, the weights from here, weights from the previous probabilities, weights from here to distribute it in this way, so that now the redistributed values are becoming like this. But the weights are these weights are increased. Do you see that, everybody? Rajan? Good, right? So
Yeah.
how do we do that? I said this is the error here. We come back to that epsilon value, that is 0.3. Now epsilon 1 minus epsilon divided by epsilon is what? 0.7 divided by 0.3. That is what the odds is. Take a logarithm of that and then take a half of it. That is what your alpha 1 is. Everybody understands now how I calculate? Go back and check the formula. You will have that. What is the formula here? It says it's not visible to you. Okay. What is this formula? It says. Let me try to post it here maybe and make it bigger perhaps. Oh joy. Control Z, I don't know, I made some mistake here. I posted it, some mistake here. Okay. So the formula, can you see this formula? I'm going to make this formula bigger. How do I do that? I thought I can make it this way. So let me do this.
Don't copy the equal to sign and just paste it.
That should be good enough, right? That's what I'm trying to do here. I'm going to take it out. I could have done it easily, I just said, like this, instead of doing all those things. Okay, let me paste it here. Oh.
No, you copy that, escape and paste it. Yeah.
Okay. Copy, escape. Okay. Oh yeah, I have to get out of this place. This is the formula. That is saying exactly what we said, right? Because this is E6, this is G16. This is G16, that's the error that goes in the denominator. Numerator is the correctness, correctly evaluated probability. This is incorrectly evaluated probability. So this is 0.7 over 0.3 logarithm of the x, natural logarithm. Okay, it's not log base 2, natural logarithm, and then half. That's what this value is. So I got the constant. Now I have to calculate the z, the z value. That z value is the one that gives me. These are the z values. D2. Once again, these are the z values. Oh, here it is. All right, so these are the z values. Remember that. Remember this. Okay, these are the z values, but we have to divide this by sum of the z values. That's what this one is. Everybody got it? Sum of these. Each of these values divided by sum of these values. Because I already done the boosting. Now the boosted values are not going to be your. If you find out some of those, let's see, find out some of those. It won't be 1. That is the problem, right? Oh, it's already calculated here. That's what this one is. This is the z value. That's why it is here. Maybe I should make it in the middle, right? In the middle. No, not that. Here. Okay. Maybe right to the right. Okay. So this is the z value. Everybody got it? Make it a different color so it's visible. Not this. I want this. Everybody good? So I got the z values, and then I z divided by these probabilities divided by z is this one. This one, if you calculate, this is 1. Now it is. I have come back to a probability distribution, but it is a re-weighted probability distribution that gives more weight to the error observations and less weight for the correct observations, right? Less weight for correct observations. Correct error, non-error maybe. Correct or non-error, which is a better? No error.
You're dividing z by what? Z by?
Z is the. These are z, remember these are z values. This is the z sum. Maybe I should write it as
z sum.
Sum of z values. Okay. This is sum of z values. Everybody is good. That's a way to that's a way to make sure that we can make a probabilities. Convert these things into a probability. That's the end of the story, because we keep repeating this again and again. Let's do next step, and then you will know you are done with this. Okay. In the next step, what did I do? Visually, I'm showing you. So I need to make, because I gave so much weight here, my rule is going to make sure that it is predicting this correctly this time. If not, then I will go here. We'll come to that. Okay. So I go here and then I find this place now. I'm showing it to you visually, but computationally, that's what will happen through this process. I'm visually explaining it, but computationally, this is what will happen. Okay. Everybody is good? Now this time I say left of this is these things, or left of this which will come. This time we were talking about what am I trying to do here? Okay. Now to the right of this is all non-targets. Okay. To the left of this is targets as well as non-targets are mixed. But the whole idea is. Okay, or not, I need to show the right picture for you, because the sequence matters. The second step is what is happening is, these are the given weights, right? So the H2 makes sure that these 3 things are identified correctly. Do you agree with me? These H2 now, right? This is the H2 means hypothesis. That means that's a tree. Okay. That is a tree. Next to tree that we find is to the left, it will identify, because these got more weights than these weights. Okay, because these got more weights than these weights, this will be targeted to be found correctly by the H2. Good? Everybody is good? These 3 things will be targeted to be found correctly by this H2, because this got more weights than this. These are looking like big monsters. These are puny, tiny monsters. Okay. Everybody is good on that? Now let's finish that computation. So what happens this time? I got this as error. Okay. This as error. I'm going to make it as error. Okay, because that's easier to think instead of saying 1 otherwise. Everybody is good? I got these things as error, but I want to make sure these things mean this 0.07, 0.07, 0.07, right?
Yeah.
So these are now going to be boosted. So again, I'm borrowing the probabilities from other sets and then, assigning weights in such a way that they get boosted. This boosting process is same. I don't have to go back there. We'll do the same boosting method here. and then we got 0.14, 0.14, 0.14. And then when I normalize it with the z, this is the second z, the sum of z values, right? Remember that. This is sum of z values. This and this color, same color, right? I want to make same color. That means they mean the same thing. Sum of z values. So let me make sure that this is this cell is something called format. 1 second. It is inside the bound. I want it to be inside the bound, okay? Inside that cell, wrap text. Okay, so this is same as this one. So these things mean the same thing. That's why I'm saying. So this time the z value is this. I divide each of this one. I get this now. So it got huge values here. This is the normalized weighted values. So with that, these things are getting identified correctly. Now this is exhausted. I went through all these things, from left to right. I went through. Now I'm going to go through this one because there is still some errors here. Okay, so let me show you. It may be here or somewhere. I want to show you the process here. I also have some definitions, some graphics that shows that which of them are getting error and so on. So let's go back to this one. So this time I found this one, but these are the errors. Are you with me? That's what I'm trying to say. The second step in we are getting this H1, but that H1 finds these three correctly. The earlier step I found this two correctly. So I got two trees. If I combine these two trees, I will identify all targets correctly, but it will make this error. This has error. So I need to find one more possibly. That's what this direction is. If I go this way, then to the right, below this is all negative. Above this is all positive. Below this is all negative. If I make that kind of rules, then I have covered this also. But you might wonder, well, these are all errors at this time, right? But if I combine all the three together, that's what I'm telling you. If I combine all these three things together, then everything is good. Are you with me? This is also, some kind of very strange looking function, right? Sine function. This is called sine function. Just simply says to the left or right, to the left or right, right? That's why it is called to the left or right, to the left or right. And to this one is, to the left or right, basically same as saying above or below, right? In this case, because the variable is running from here to here, okay? Above or below. So if you combine these things, that means you are, eliminating this part. You are eliminating this part. That's what this type of function does it. Don't worry about it. These are all things mathematicians play with this. The point is this bent curve, this bent line, piecewise linear line. This is piecewise linear. If this piecewise linear is a separator or a predictor that predicts this versus this. Are you with me? Everybody? Rajan said, Rakesh?
Yes, sir.
Yes, sir.
Soumya said yes.
Yes, sir. Yes.
I remember, I'm not expecting that you will remember this 1 week from now. Maybe you will not, but I think you will remember how the boosting process happens. Because if you understand this, you have a better feeling to communicate with others, right? But from going forward, you are going to do the codes. Computer is going to do these things for you. You don't have to do all these things by hand. That makes it life easy, isn't it, Rajan?
Yeah.
Right? And that's what you want. That's what everybody wants. That's what I want also, right? But it is good to know these little logics. Somehow we as humans develop these ideas so that the machine can learn. The machine doesn't know how to devise this, design this. But if I make this way in these steps, machine knows how to learn. Machine doesn't learn. We make the machine to repeat certain intelligent process. It's really a hype that machine is learning, right? It's not, machine is not learning. We made an effort to create certain algorithmic computational steps which can be implemented in machine. That's what it is. It's in fact machine learning. Instead of saying machine learning, we should say machine implementation. That's what it is. It's a hype. You say machine learning, artificial intelligence, these are all hype. Really, it's hype. I'm just opening up the guts and showing you, right? If you are becoming a physician, it is very ugly when you see inside. But when the human body walks and acts, it looks beautiful, right? That's a hype. But the real internal is something that is actually energizing you. It's a very ugly engineering inside. I'm opening up and telling you. The hype is that it's not a machine learning. Please remember this. It is mission implementation of a very smart human algorithm. And you need to know those things. Only then you feel confident talking to people, right? You have to be, because you are the master, not the machine learning algorithm is not the master. You are the master, you are the guru. Are you with me? Samya? Make
Yes,
sense?
sir.
Goshali?
Sir.
Okay.
Yeah.
Right.
Yes, sir.
Excellent.
Yes,
So
sir.
we finished, add a boost. There are many other boosts are also there. We don't have to worry about it. The main point is the add a boost does a great job, and that's what I want to show you quickly. So this is what I wanted to share it with you. That these things, these are plus initial plus, and that's become plus, and then I also have a few other slides. But the main slide here is this one. I will come to the codes. Okay, this is the codes part of it. We'll come to that. Add a boost for text categories. Add a boost has the least error. Look at this one, percent error, right? This is the percentage. Are you able to see this one? Percent error, right? There are so many algorithms are worked out, and add a boost has the least. It uniformly beats all the other algorithms. Naive Bayes, whatever, PR, TF, IDF, sleeping experts, Rokio, but add a boost has the least error. That's why add a boost became very popular. Everybody? And this bound, actually, the mathematics, the way we devised it, as you do more and more, you talked about it, this is the mathematical bound, Rajan. This goes to 0 as you increase the number of trees. That's what this means. Because exponential of some positive quantities, right? These are all positive quantity. Okay? Exponential, because square, right? Square means positive quantity. So exponential of, exponential of minus of some, keep on adding positive quantities means this keeps on going down to 0. Are you with me now? That there is a mathematical proof that add a boost works out well. And that was an answer to you specifically because you asked a wonderful question. Okay, what happens when it's a non-linear data? Right? Doesn't matter what data it is. All right. So I want to move on with this one. We have kind of solved that problem. So let's just go do some coding, right? Ready? These are all things, don't worry about it. It's just irrelevant. We are all called practitioners. We are practical people. We care about, even though I teach you mathematics, literally I care about, I push the limits only to some level where you are very comfortable, very knowledgeable, very communicative. Okay, I stop there. I will not go, oh, let's do this mathematics. No, we push enough of it. But then to show you are a great master, you can communicate with your analysts, with other people, so that you can get your work done. Correct? That's my goal. That's why we are called practitioners. Okay. Now we have done up to this. Let's go. I sent you. This is a very important. I sent through Supriya a workbook. Okay, that is called Fisher-Iris case study. Okay, Fisher-Iris case study. We want to go through that. Console. Let me. You can open that. Let's run that one. Okay. We start at 9, so before 10:30 we'll finish this, and then so I finished boosting the first level boosting. There is more things are coming. Okay, but let's finish this one practical example. How about that? Open that, the one that I sent it to you. Are you ready? Everybody is ready with your R and
the Fisher case? one?
Fisher Iris case study.
Okay.
Correct? You got it, right? Rakesh? Today from Supriya, you all got it, right?
Yeah, I have emailed it to everyone. You guys got it, right?
Yeah.
Yes, we got it. I'm downloading it now.
Open that
Thank
in
you.
on. There are some new things here, Supriya, for you also. So please watch out too, okay? For you too. Because we are doing multiple classifications.
I'm getting this along with you. Or I've been already working on it since evening.
Oh, okay.
While you were giving the lecture, I was actually running the script at my end, working with the
Okay.
files and everything.
Okay. So anyway, sometimes we do little additional things. Now here's one of them. So I thought it's good because I want to address, how to know about, the graphical issues about, understanding, visualizing, parts of the tree, parts of the forest, full forest, and so on. Okay, as much as possible. Now, if you open it, there are lots of different packages you all have to run. Make sure that you run through this one. If you don't have it, you have to install this one. So can you run the first part, please? The first part is what? Install required packages and then call in. You can't just call in the library dev tools. No, you have to call. You have to do the install.packages dev tools and then library, right? Go, Shali, correct?
One second.
Take your time. Take your time. Install each of these packages. Make sure.
Yeah, I think we got the HTML file. So,
Oh, you got HTML
Yeah.
file. Oh, okay. Yeah, maybe that's what I did because it is easy for me to do the work without running.
yeah, so we have to copy and paste it in the.
You want to do that? Can you can do that, right? That's okay, right?
Yeah, that's right.
So run, but when you do the library, make sure you have to install each other package. Are you ready, Soumya? Can you do it?
Is there the Cleveland dataset? That is not there.
Oh, data set.
Or can we download it?
I'll send that.
Cleveland dataset.
I'll send that one. Thank you very much on that one.
Okay.
So I will answer to that whole group. Okay. Whole group, I'll answer it. How about that? This is a very important assignment because we also talk what is called hyperparameters. Random forest, boosting, hyperparameterization. Hyperparameterization means, see, we don't know how many trees to build, right? If I said default is 4, but what if 4 is not the best? We have to do searching, right? We have to do the searching of what is the best number of trees, right? Number of variables to select per tree. I'm sorry, number of variables to select per tree, right? Default is 4, but maybe 3 is better, maybe 2 is better, or maybe 5, maybe 6 is better. If I have 13 variables, I have 13 variable example. Maybe all the 13 variables have to be used. Then there is only one tree, but nonetheless, in a loop we can put it. That is what is called hyperparameterization. Everybody got it? Understood? Go, Shali. Do you understand what I'm saying? What is meant by hyperparameterization? There are so many parameters we have to fix. So it's not just enough if you call random forest and do everything in one shot. No, we have to search. It's a big deal. This is the big deal stuff. People don't teach this. No, normally other people. I'm sorry. We do teach in Northwestern also because that comes under machine learning course, whole course for 10 weeks, just machine learning alone. Okay. So, but we are doing it with what? Maybe 6 sessions with you, 6 meetings with you. All right. So let's do I'm going to send you the same email that Supriya sent. I'm going to attach the data set. Okay. The one data set you need, that is the hot condition, predicting hot condition. Okay. That's one data set is the only one you need. Am I correct, Supriya? Let's go back and check.
Yes, sir.
Fisher Iris data is available with the generally.
What is that?
Okay.
Normal dataset is available.
I'm sorry. Rajan is saying something.
Iris dataset.
Oh,
Sorry.
Okay. So, நீங்க என்ன சொன்னீங்க சுப்ரியா?
இல்ல ஐரிஸ் டேட்டா செட் நம்மளுக்கு ஈஸிலி கிடைச்சிரும் சொன்னேன்.
It is usually there. So I'm not. I don't know. I don't have to send it to you. But attached is the Cleveland art study. Okay, it's a very nice data set. It's also can be used for multiple classification. Okay, Cleveland. Okay, Cleveland. It's a place name, so C should be uppercase. I'm going to attach it here. It is ML. Art study. So okay, I will go to some other place. I know where it is. Okay. Let's receive that, and then we can go over this example. Okay, this is very important example for reasons like hyperparameterization. You can even repeat this, Supriya, one more time. It's okay, but you know you can also do another example. Okay, another example.
Yeah.
So please make sure everybody installs DevTools, Plottrix, Random Forest, Tree, 5. Don't worry about 5 for it. It won't work. Mass, dplyr, tidyverse, Caret, and CA tools. All these things have to be installed. Okay, because there is a lot of work here. You know, it's a very big assignment. Okay, very big workout. So once you install those things, please let me know. Here. Okay.
Thank you, sir.
Hello. So everybody installed the packages?
No, sir, doing it.
Doing it, okay.
Yeah, so the FIFO doesn't work. I tried all the methods.
No need.
Okay.
So see, I kind of commented out.
Sure. I'm just trying alternatives and everything, but then
Okay.
don't miss out.
You are able to see, right? These commands. So we have 1 second. Hello, welcome. All right. So when you are ready, you can tell me, okay? It takes a lot of time to install
Yeah.
this.
I just yeah, before starting, I just want to tell you one thing. You know, I'm having a little big screen, so I might I'm looking somewhere else, but I am looking at the screen. So I just want to clarify that.
I'm sorry. Are you ready or not? You want?
Yeah, I'm ready. I'm just telling, as I'm sitting in front of a big screen, I might look like I'm looking somewhere else.
I cannot understand
No, in the video.
what the problem is. What the video is not coming through. Is there any problem receiving my stuff?
No. From my end, I'm telling you, I might look like I'm looking somewhere else, but I am looking at the screen.
Don't worry. No worries.
That's okay.
Okay. So what about Goshali? You installed everything is okay. Soumya. Okay. Soumya is okay.
Yeah, done.
Rajan is okay. You still need time.
Something else comes up there with air quality. Do we have to do that also?
Yeah, please copy that example. That's good.
Whatever is
It's
happening.
just 2 or 3 lines. It's a good example. Please copy.
Okay. Give us a little more time.
Okay, that's fine.
I know, sorry. I was trying to copy it in an RMD so that I can email it to these guys. But believe me, I've been doing it for 1 hour.
I thought,
Sorry, sir.
that, this is good enough. And I don't understand also anyway.
I know. It's all right, sir. No problem. It's
So
all right. It's all right.
I can, so there is a RMD file. I can send also, no worries. 512 AM. This is what I can send it to. Okay. How to read the RMDs. Yeah, I will do that too. One more time. But doesn't matter. You still have to install the packages. That is where it is taking time, in my opinion. Okay, because you can copy
Yeah,
the.
no, that. Yeah, the script can be copied, and the one installing those files that takes time.
So it takes time to run the packages. Okay. All right. When you are ready, you can tell me, Rajan. Hello. I'm just teaching here. I hope it's okay. No problem. Welcome.
People who have come to your place.
Yes. Okay. So when you are ready, you can tell me. Okay, Rajan.
So I'm getting an error in middle. It says that CH is not found.
No, that is the data that I sent you to download it and put the right folder name.
Oh, okay. So you sent some data now.
Just I send that data. You can come and see this room also if you want to. We are selling a house.
You get the email, sir? Everyone? Everyone got the email of Cleveland dataset, sir? I just sent now.
Okay, got it.
Okay, great. Just reset the directory to the path where you're saving the file.
I mean, because it has some new codes, I wanted to just explain, be part of this today.
You're laughing like that. Hey, just stop me. Are you making my ball today? Not ball again. Fun. What did you say? Are you making ball? You like fun? Why do you like it? Because
This is a good example for understanding factor variables, actually. Yes, sir. Cleveland dataset is a good example for factor variables.
All right. How is it going? Go, Shali.
This doctor.
Finished?
No, not teacher.
Okay, not yet. Just taking time. How about Samya? So who has finished?
Maybe you could take 10 minutes break. You could take 10 minutes break until we finish this part.
Come on, it's okay. It's all right. No. I mean, it takes time. Don't worry about it. Maybe you are right. I can be a little bit more, away from this place for now.
You could probably go and take care of the people who come to visit your place until we finish this part. Supriya, I'll need one help from you. Whenever you finish with this RMD file of this, I mean, I'd appreciate if you could send it across.
Yeah, sure. Don't worry.
I straight away started putting it in the R file and not the RMD. So that's something wrong which I did.
Everyone from here on, kindly make the practice of creating an RMD file, because it's easy when you're going to be doing, okay? Chunk wise understanding, data flow, correction, debugging, everything becomes easier. All right?
Yeah, I did a mistake.
Get me some water.
So please send me whenever you're done. Huh?
No.
Yeah.
Yeah.
I have to still receive assignments from everyone. I've been bugging everyone of you. I know that one is done. Please
What
submit.
We have assignments?
Yeah, right. I have sent it over.
I thought you were a good friend.
Nah, it doesn't work like that. Sorry. I'm being very nice to you. That's why I'm making sure that you guys are finishing it.
If you follow all my guidelines, you will be super data scientist. Believe me. In a
No doubt
short
about
time.
that.
That's unbelievable achievement.
I second that.
Huh?
I second that, I said.
You have to practice, you have to spend time, you have to commit. Rakesh is ready. Rakesh,
Bring the water. I'll give you.
everyone should be ready.
No,
This
no.
6 months will be one of the best times. And follow guidelines. There are tons of intelligent information I'm giving you. If you do it yourself, it's going to take 10 plus years. I'm telling you seriously. All the little details I'm giving you here and there, so many little details. It takes so long. We are very happy that you came to us, but do the work.
Yeah.
Follow that. Spend your time. Commit. You will be really very good if you practice. From then on, it's just about practice. But you have a reason, confidence to practice what I tell you. What you should practice, what you need to practice. So please, besides this, also, even outside, work, spend time on the topics. Go through the same example many times. It's worth it. It's worth it. And probably there are typos in my, you should be able to find it because you're going through so many times. That is the level I want you to be there. Okay? Are you hearing me out, everyone? Okay, let's continue to do. As far as possible, I also put the notes here,
Yeah.
For example, what is meant by proximity? Proximity refers to how often two observations are in the same leaf. Okay, so that is also noted in the output so that we can do some visualization. Okay. So like that, there are as much as possible, lots of details are there. We give you the mathematics, we give you the codes, we show you how to do. Supriya spends a lot of time with you. I spend a lot of time with you. You can't get better than that. So where are you guys now? Update, everybody, update me.
80% done.
80%. You are talking about installing the packages and library, calling the library, right? Okay. Still working on it.
Yeah, I am done finally.
Very good. One person done. Everybody has to be complete, right? Completing so that you can follow other commands. You can take that 2 minutes break if you want. But we'll continue, okay? Those who finish early, they get more break. Sorry.
You're done, sir.
You're done. Very good. Rakesh is done. You're able to see my enlarged HTML file, right?
All done, sir. Ready.
Everybody's done. Soumya,
Yes.
excellent. Gaushali,
Yes, sir. Yes, sir.
Yes, sir.
excellent. Very good, very good. So you do the next command is this one, right? We're going to do basically just explore the data, right? Data iris. You have to run this chunk. If you run this, you are accessing the data iris, and then you are checking out what the data has. It has, right? That's what structure is, str. And then you are creating using create data partition function from caret. You are going to create whatever the training sample is. You know, you are basically dividing into 50-50, right? 50% goes into training, 50% goes into testing. Iris test is minus in train dot comma means, you know, don't include the indices rows from in train. That means that goes into testing. Everybody's good so far? And then again, I'm checking structure iris. So you can run this one block. Good. Do you want me to copy and paste it, or you know, you can just do it? Run it. Everybody ran it. Rakesh did it. Rajan did it. Gaushali did it. Right? Yes.
Yes, sir.
Yes. Okay. So you kind of understood what's going on there. That's what basically you are seeing here. These things. Okay. Right. We will, after you finish like me, you can knit it into a HTML file. Right? You can knit it as HTML file. Okay. So these were all done. Now I'm going to the library random forest, and then I'm going to do this a little bit more advanced. Remember, species. That is the class of 4 flowers, right? 4 iris flowers. 3 iris flowers, 4 attributes, features. 4 attributes, features, 3 types of flowers, right? 3 types of flowers, 4 attributes. Okay. And so I'm using the data iris train only, iris underscore train. And then species as a function of all the 4 attributes, okay? Number of trees I want to build is 500. I'm going to use proximity measure also to as output for us, okay? That tells you how often 2 observations are together in the same leaf. That is an indication of how close they are in terms of prediction. Remember, it's not in terms of their distance, in terms of the prediction. So we run that part. Okay, can you run that step next chunk, everybody? Did it, right? Rajan did it.
Yeah, I executed entirely to the end also, to the final.
Okay, fine. Everybody doing it to the end of it?
Yeah, I thought that
Okay,
was
fine. So
what we were supposed
let's
to
go on
do.
and explain this one. If that's the case, I will explain to you. How about that? Huh? I will explain with this output. That's what the full output
Maybe
is.
you could maximize that.
Yeah, he did. No, you want more. How about this? Is it enough? Is it enough? Okay. So we run that, and this is the forest that we built. Very important thing. I'm going to tell you something here. So it ran this random forest, and for 500 trees it created. Number of variables tried at each split is 2. Number of variables tried at each split is 2. Okay. Okay. Now there is something called OOB estimate of error rate. OOB estimate. That means out of bag. Please write it down. Out of bag. OOB means out of bag. What does this out of bag means? So listen very carefully. There is a training. There is a testing. Testing is set aside. Correct? Testing is set aside. That observation, testing observations are just set aside. Now, how much we set aside testing? 50%. 50% for training. In the training, we ask certain number of observations, certain portion of the observation to be used for every time we take a sample, build a tree. 2 things we do, right? We take a sample of observations in training. We take a sample of a number of variables for building a tree, right? Every time. That's how we build a large number of trees. So that when we set aside, when we have this 50%, so out of this 150 observations are there in the population, 75 are set aside for training, 75 are set aside for testing. Out of the training, we again split 50%. This is default, okay? 50%, you can set that number also. 50% for training a model, and remaining we set aside within the training data set as out of bag. So that's for validation. So out of bag, please write it down. Out of bag is same as validation. Okay. So what is this error? This error is we did not use this sample. This is actually we predict the error based on the training forest we built. Remember that. Training forest we built. And we use finally to create the confusion matrix. This is confusion matrix. Remember that. Huh? It says that confusion matrix, right? You know what is meant by confusion matrix. This is a 3-class confusion matrix. So the correct ones are on the diagonal. Incorrect ones are off diagonal. So there is 3 observations. This is 3 observations. This is actual. This is the predicted. 3 Virginica. 3 versicolor is predicted incorrectly as Virginica. 2 Virginica is predicted incorrectly as versicolor. Those are the 5 errors. Okay. So this is the confusion matrix. This is the Wood error. 6.6. So we are able to remember these validation samples are not used to build the model. Only training is used to build the model, but validation is always testing. So for a sample we take, we do the model, test it for the OOB, out of bag sample. Test it, I shouldn't say test it, validate it. Right word you have to use. We validate it with the OOB sample. Okay, and that is what when we do the average OOB estimate of error is 6.67 because there are a lot of trees you built, right? So that is what. That's a good one. 94% accuracy, isn't it? 94% accuracy. Now, what else we do? So you learn something about the OOB, remember that. But then OOB, that is out of bag error. Now we want to see some trees, as you said. So let's go and just print only the last 5 trees. Okay, last 5 trees only. That's what this is happening. So these are the trees. We get the trees, we print the trees, right? So that's what this one is. You have to know how to read these trees also. So let's do that a little bit. So what we are saying is that the first node, top node, is left dot. It's called second node. Left is number 2 is left node. Number 3 is right node. Okay, we code the nodes also here. So what helps us to split? The sepal width helps us to split. Less than 3.25 is left node, goes into 2. Right, it goes into 3. Okay. If it is not terminating, we give the symbol 1, letter 1, number 1. If it is not terminating, if it is terminating, we give number -1. Okay. That's it. These are all the only information you need. Do you agree with me? Okay. Okay. That's all you need. Now, and then you can see at the end, it will always be giving you some class because there is no split there. You know what the class has to be. Okay. So that is how you read this one, and these are the observation splitting points. You see this one, split points. Everybody's good? How to interpret the whole tree. But this is only one tree, remember that. Only one tree, and I have printed it as graphically here. You wanted to see the tree, okay? But probably you also want to see the forest. I agree with you, okay? But forest is harder to see because we are going to keep, what is meant by, putting a blob of things. It's not clear, right? So we have certain mechanism to think about and see forest. But this is the physical, this is the actual printout. No, same thing, I took it out. Look at that. Same thing, I took it out. 3.25, left is So we take the sepal width at 3.25. Left is code 2, node 2, right is node 3. And then what happens? Let's go there. You can combine these two also to figure it out. So 3.25 left is, then we use petal length. That is, left means less than 4.85. Right is this length, this node, and this node is now here we start with sepal width, now petal length, and then sepal length we use. Eventually it is virginica to the left, and then right side is versicolor. Good, everybody? This is looking at one single tree. You do that. This whatever is here graphically, which is easier to read, is also printed like this, because computationally this is what is done, and from there we translate this, in this graphical form using all these packages. What package I got? I think Skinner 927 repertory. Okay, repertory, and it's not, the package is not released, so it is coming under dev tools. Okay. All right. So we print actually more than one. So this is the next tree. Well, 496, 97, 98, 99, 500. All those five trees are printed here, basically. Okay. And how do you, for each tree you can use to predict observation and find the OOB error, right? OOB error, right? How do you do it? You take each observation, run it through the tree, and see whether it is correctly predicted or not. This is the decision tree that tells you this is what you should assign, but the reality may be different, right? And so you take an observation, run it through those observation, values, and then you will end up here, or maybe here, or maybe here, maybe here, maybe here. One of these things, right? It has to be one of these endpoints. Okay, and if you fell correctly, then no error. If you fell incorrectly, suppose it is a setosa, and then you end up here, no, there is no error. But if you end up here, let's say versicolor, it is saying it is versicolor, the observation based on this algorithm, based on this tree, then we say it is incorrect. That is how it is used for prediction, right? So I have given here 5 trees just to show you and how to interpret. Any questions?
So here, two variables at a time is how it is taken here, the diagram.
This is 2 variable, right? Actual multiple variables are say this variable is used, this variable is used, this variable is used, this variable is used. So all these 4 variables are used to make the decision actually.
Because in the results we saw it takes 2 variables at a time, right? So what does that mean?
Okay. M try. Actually 4 let me go back to this one. It says 2 splits. I mean 2 variables. It said that, right? M try. Actually I should print to know what is the M try is. That must be a way to get all the parameters out, right? So let's go back to this one. So this is for printing. It says number of variables tried at each split. 2 variables. Okay. So we take 2 variables. Let's say let's take this one. So we take 2 variables, compare the one that helps us to split, we take it. Okay. Then move on to the next level. But this is not a boosted tree. Remember that. It is just continue to build tree. Okay. So this one I have to verify. I have to verify.
Okay. At each.
Yeah. I have to verify this.
I can see. I can see. At each split, it takes 2 variables. At each split, I can see in that.
Where is that? Where do you see?
The tree which you showed.
Where is that? What you're saying?
The tree diagram.
In the diagram. Okay.
So in each split, it is taking two at a time. So for the first split, it is taking petal length and petal width.
Mm-hmm.
the second petal length split, it is taking sepal length and petal length. So I think it is taking two variables at a time during each split.
Yeah, it is. Yeah, I think there is a little bit of confusion here. M try versus number of splits. M try versus number of splits. The number of splits is 2, but M try is 4 right now. That is, the random number of selections of variables is 4, right? And that's because it's only 4, it takes every time 4 variables. But then it uses 2 of them to make a decision to split. Okay. Now, so you see some of these samples, you can print them, you can go through for clarity and so on. Now let's take another example. I have 3 examples here. Okay, another example, air quality. I don't know. Okay, so this is where there is something called, I told you yesterday, Shapley values, right? In other words, there are many ways to look at the importance of variables. There is also variable important plot. Okay, we don't need that for iris dataset, which is only 4 variables, which has only 4 variables. Okay, iris only has 4 variables, so no big deal. But there are problems where you have many variables. So you want to find out what variables are important. There is a method that is available for you called var imp plot that ranks the variables. Yesterday I showed you, right? The Boston housing problem, right? Housing estimate, the median price of the house, how to predict. That is one of the methods. But then recently people wanted, they still don't understand it is what is meant by this variable importance plot, because there is a variable depends on other variables also, because it's all interaction, highly interaction based decision rules, or algorithms, high level interactions. So people don't understand that, they were looking for more and more explanations, what is called the interpretable models. So they were asking, can you give me visually how variables are integrated out? When I see temperature, in this case we are talking about this example, air quality example, we are printing what is called in terms of knowing the importance of variables, what is called the partial plot, because given that variable, you want to integrate out all the other variables interaction with that, so that you can get the pure effect of that variable. Are you with me? Okay, but it is very difficult to understand because there are so many ways the variables are coming and interacting in a random forest, right? In each tree, it could be different variables interacting with them. So can we get some understanding about the importance of the variable? That's where they started defining partial dependence. Shapley value also is in the same class of interpretability of the forest, random forest. Okay, it is another way of looking at it. The point is, there are some methods I'm going to talk to you, but I don't have a Shapley value here. There is so much we can spend time here. There is no, I don't have time. I do one day whole random forest and bootcamp course. Okay, bootcamp course. So that is not possible. This is good enough for you. Okay. So here is an example. So this random forest has, if you want to know, this is the data, right? 111 observations are there, and then 6 variables are there in that air quality data. Okay, so the air quality here, what we are trying to predict is ozone level, solar or wind, temperature, month to day. Okay, so we are predicting ozone level, as that's what it's called, air quality data. Ozone level using all the other 5 variables. There are 6 variables using all the other 5 variables. Okay, so we also print the importance of the variables also. That's what importance is true. So here is the important variable. So it says this variable importance include node purity, percent increase, node purity. Okay, so I didn't teach you node. What is meant by node purity? It is related to the the entropy. Okay, I will send you the notes separately. I'll write down the definition, what is meant by increase. Okay, for you, I'll do that. But what I want to go and explain is that this partial dependence plots, because this is another way of looking at variable importance. Okay, and also tells you at what levels of those variables they are becoming important to explain the prediction and the error, right? So it says, for example, up to 70 degrees, it's not it's not really explaining much up to 70 degrees, right? But then afterwards onwards, it has implication on the temperature has implication on the air quality. That makes sense, am I right? Right? That's why in colder places, you have a less air quality problems. Okay, of course, it's also connected with the solar effects, day or month, because the other cyclical production issues, industrial activities and so on, right? But I'm just telling you, if the wind is very less, it's not going to spread the smog all over the place. So again, you can see that. Okay, so there are these variables, you can use it to explain the pure effect of each of the variables in the model now, because you are integrating out the other variable effects in the interaction model, and the trees are interaction models. I'm giving you a way to interpret using partial dependence plot, which you can get like this. This command, it's called partial plot. It's part of the package that you have. The package is whatever the package we are calling in will help you to do that. We are already called in lots of packages, so you have to use all those things, okay, to help you print these partial plots. Is everybody good in terms of interpreting it for your manager? Now, let's go to the Cleveland Hart study. Do you want to
Can we take a break and start? Or? Can we take a break and then start? Because this will take time.
Yes, okay. Let's take a break. 10 minutes or 15 minutes. Okay.
Yes.
Okay.
Thank you.
Okay. So, it's very, very important. People will show all kinds of results. You have to think always very carefully. What is validation? What is testing? And testing will always be less than the less predictive and more error compared to validation. Of course, training is going to be perfect because it is so finely cutting the dimensions for every dimension. Okay. And then there are other types of measurements. Remember, these are all things you have to learn. Sensitivity, specificity, and this is for the training data. Come in. Good morning. These are all for sensitivity, specificity. These are all the measurements I wanted to learn. I have shown one Wikipedia tabulation, if you remember, in blue color, red color. You remember that? I showed you that, where there are a lot of terminologies are there. I will send you a slide about these meanings to you later, if you want to recall. Okay?
It comes in the confusion matrix, right?
Out of the
logistic regression comes.
Out of the confusion matrix. But you have to remember this thing. But it is very easy to remember the way if you follow the way I give you. Okay. So you want sensitivity to be high, specificity to be also high. 1 minus specificity is false positive, which means false positive will be low. Remember that 1 minus specificity is false positive. Okay. So this is the confusion matrix for the test data. See this one? Data is test. This is the confusion. Now you see there's a lot of errors, right? That's why it will happen. And so one thing I have to send is one slide that compares all these terminologies. Easy to remember. Is saying it in English, no mathematics and all. Okay, saying it in English. I'm going to send it to you. Okay, remember that. Now I want to bring the issues of what I told you is hyperparameter optimization. Okay, how many number of variables to select, and all kinds of things are there. Hyperparameter optimization I want to bring and talk to you. And also there are many ways to do the, call the metrics. You can call for AOC, you can call for accuracy, you can call for all kinds of things. There are other parameters also you can mention. So when I run this code, and this time I'm defining method called CV, cross validation. Please write down this sentence. The golden rule is always cross validation. The golden method to validate your, build the best model is, which is not over predicting, is cross validation. Remember that. If anybody does the method, you have to ask them, did you do cross validation method? And here I'm going to show you how to do the cross validation method for random forms. These are all part of parameterization ideas. But if you say cross validation, you know what is cross validation. I taught you before. You have to split the, if you have the total sample, you can, if you say 5, that means you have to split it into 5 parts. And one part will be validation, 4 parts will be testing. Okay. So you will do 5 times. 5 times split, that means 20%, 20%, 20%, 20%. And then it repeats the model 5 times. Okay, that's what it means, cross validation. And then we are saying I want accuracy measure. That's what this one is, right? The grid search method, grid search method means it will search over the various parameter values. It will search and print all our answers, the errors. Look at this one. It tried m try is equal to 2, m try equal to 11, m try equal to 21 for this data set, right? For this data set. And when they tried m try equal to 2, it's got accuracy of 64. But remember, it's a 5-class problem, right? 5-class S1, S2, S3, S4, 5-class problem. So accuracy means only the diagonal. The non-accuracy are off diagonals. Oh, whoa. Okay, something happened to my computer. Non-accuracy means off diagonals. Okay, that's what the 64% of them are correctly placed on the diagonals. That's what this means. Everybody's good? Rajan?
No, can you tell that m try and kappa one more time?
Number of variables selected randomly to build that. When it tries the number of sampling, number of variables 2 at a time, this is accuracy. Number of variables tried is 11 variables. It is this one. Okay, number of variables. This is it's a little bit confusing to me because it's 21. That's 21, right? Number of variables m try is 21. It says. I have to look into this one. What it is 921. I need to correct. The final value used for the model was 11. Okay, 11 turned out to be the best. Okay, because you can see that accuracy is high. Okay, let me get back to this one. 21 here. But for now, you can see that 11. I just ran this today morning. So I wanted to share this hyperparameterization. This is the first time we are doing it for students in these notes. So this will help you by doing this. It will help you to figure out this m try. Earlier it was m try was full default. Remember that. But here it tries different.
Sir, accuracy. Sir, accuracy here we got like which one is the good?
This is the good one, right? Accuracy, maximum accuracy one. And that's why the model itself says the final value used for the model is m try is equal to this line. it prints out. It prints that out, right? Now, we want to try all these different possibilities. You know, M try is 1 to 8. If you want to try, this is the better way, Rajan. I would rather forget about this one, right? This is the better way because you are going through systematically in a grid search, 1 variable, 2 variable, 3 variable, 4, up to 8 variable. Do you have to stop with 8 variable? You can go beyond also because we are up to 15. So again, I'm building the model num as the function of all the variables, but then it is going through a tune grid. It says tune grid is equal to tune grid. Tune grid is the one of the parameters, and that is set here. That means tune this for various M price. Okay. And importance is going to build. Node sizes, no, we want to know not more than 5 observations, node size. These are all the ways to control. This is why it's called hyperparameterization. Okay. And number of trees is 500. This time I am giving again 500, and then I'm asking for the print of this one. This is the print of this output of the model. It is printing the M try 1, 2, 3, 4. All these things are random selection of variables or attributes or features. So Gaushal, you tell me which model you will select. Don't look at below which model you will select here. If you use accuracy, maximum, the one that maximizes accuracy, right? So it turns out to be M try is equal to 6. Everybody's good? And that is what it printed here. That's what it printed here. The model itself prints for you. I mean, the R itself prints for you. And then, oh, something is going on with my computer. I don't know. It just blinks out again, comes back. Sorry. Okay, so I want to see what are the other things available created by the system. And you can see these are all the things that are created by the system. There are so many things you can take a look at it. All these things are defined in your what is called vignette. Vignette. Vignette means the one that talks about the package, all the little details. There's a vignette, you can say a random forest, it will give you all terminologies. Everybody's good? Now I want to take the best tuned M try. Welcome. Best tuned M try. I take that and then I want that model only. More details. Is that good? So I take the best M try from the random forest M try. Best tune. Best tune has this, the M try value. That is the 6 actually, right? It turned, you see, remember that 6, the best model Gaushal, that turned out to be number 6. Now we take that number 6 and then apply it to extract the model that we want. That is your best model. I understand how to extract the best model. Okay. So and then we do. Let's take the best M try from the previous search and now find out the maximum node size. So the grids are going, one is best try, the other one is node size, right? One is best try, M try, the other one is node size. We take the best try, and then let's say best tries are 1, 2, 3, 4, 5, 6, and so on. The 6 we take, and then within the 6 we want to search the best node size. Are you understanding? That is what this is happening now. I'm saying node size will give 5 anywhere from 5 observations per node to 15 observations maximum. So that is what the grid search is about. One dimension, you fix one thing and then you search on the other dimension. Okay. Usually start with M try. Everybody understands what I'm saying? Everybody understands what I'm saying? Rajan?
But why are you fixing from 5 to 15? Any particular reason? Or
no, it's saying, if you want to put from 3 to 15, that's fine. Do you want to put 1 to 15? You can also do that. But is it a good idea? One observer only you use per node. Some people try to do that also, but you can just put 3. Something like 3 is good. Starting 1 by, we do 5. Okay. But you don't want too many observations because you want to give more opportunity to split. So again, we are calling the method is random forest. Data is training data. Num is your modeling category. 5 class category. See, that's the beauty of this random forest. it is also doing 5-class prediction, isn't it? It's a multinomial right now. Okay. And then tune grid. Hello. We do the same tune grid. In this case, we are talking about we take the best M try, and within that we are looping it. Remember that, huh? We are looping it, and we are doing node size 5 here, but then it will change for C in this. Somewhere C is coming. Okay, it will change. Now every time I'm using only 450 trees. Every time I'm using only 450 trees, and then I store the best model result, max node result, into the current iteration, and then store max node, and then the results will be resamples, max node, and then summarize the results M try. Results M try is the resamples. Within that we are selecting the max nodes, the maximum, the node that matters in the solution. And here it is, the models 5, 6, 7, 5 to 15. You remember the node size? These are the node sizes. Okay. Number of resamples is 5 because that's what we started with, right? Number of resamples is 5. Right. The results M try, object is good results M try. We are summarizing it. We are doing 5 times resampling. Okay. So here the accuracy is when out of 5 times resampled, accuracy is minimum is this, median is this, mean is this, third quartile is this, maximum is this accuracy. So you want probably use median to be a model selector, Gaushali, right? Somewhere we need to use this to select the model, best combination of M try and the node size, right? Isn't it? So you can use any one of these, but which one is better, you think? I'm thinking median, isn't it? You can use mean also.
Yes, sir.
So if you look at this one, which is the best model, there are a few of the models are best, right? Look at the 72.72. 0.7272 seems to be the best. This one is all. So it could be 7, 9, 10, 11, 12. All these things are possible if I use that one. But if you want to look at the minimum achieved or maximum achieved, let's take the maximum. If I say maximum achieved, this is 75, this is 77, 7, 8, this is 77. Okay. 7 observation 77, 77, 2000. This is the maximum. So we have to make a choice here. Whatever it's okay. Huh? Okay, do you want to say something? Go, Shali.
26 in 12th row.
I'm sorry, I can't hear you. Repeat.
Yes, sir. The same what you told, like 77 is the best.
Okay. So there is a measure called kappa. You will see that too. Listen very carefully. Kappa gives you what is the incremental effectiveness over randomness. Am I making sense? Incremental effectiveness over randomness. Okay. So because oftentimes it's not equally 50% is the randomness. It's not 50% randomness because it depends on the incidence rate. If the incidence is both of them are 50-50, now we are talking into the, we are getting into the area of imbalanced data. So some classes are less than 25%. See, if it is five classes, it is not 20%, 20% sample, right? Some of them are high. I think H is very high, right? H is very high. S1, S2 are all small numbers. It's an imbalanced sample. So sometimes, especially when you have imbalanced sample, kappa is useful to measure also. So we are getting into all kinds of these measures. This is the tough area. This is where you become an expert and show that you are an expert. Okay, and you have to do it many times. Many times you have to review the definitions, internalize, apply it, review the definitions, see the output, internalize, apply, and communicate. That's the only way you will get there. Okay, everybody's good? Everybody's good? Good, thank you. So the main point is that there is also the kappa measure you can use because if it is highly imbalanced data, kappa becomes very, very important. Highly imbalanced data because now your incremental effectiveness over the imbalance data. So if it is already 70%, accuracy is 80% is not that great. Do you agree with me? Not accuracy. That particular sensitivity for that particular class, 80 is not good enough because it's already 70%, 75%. Am I making sense? Yes. So you have to use kappa-like measurements. So we are into the very gray area, but how do you avoid this gray area? Practice, internalize, think about the definitions, understand, oh yeah, it makes sense, and you have to apply it a few times, then only you will know. So let's see, if I use the kappa here, again I'm going to take median. Okay, if I use the kappa here, which is the best here, 56, 57, this is the best, 5707, these two are best. 10 or 12, node size 10 or 12 is the best. And we saw here, accuracy wise also, we saw this one is 10 or 12 is okay. Both are good. Okay, so if I combine these two, then I have only two possibilities, 10 or 12. But I used median. You could have used mean also, but median is more safer. Okay, or third quartile. You can also use third quartile. More safer. If I use third quartile, actually 12 is the one that comes out. Am I making sense to you? Why do I do third quartile? Because I want to increase the, the maximum possible situation with the, with accuracy. In this case, it is kappa. I'm sorry, kappa. And I can do the same thing also here, third quartile. If I do third quartile, 75, 76, this 12 and 13 are the best. So obviously, if I use, third quartile for both this, then I achieve 12 as the best. Everybody got it? Okay. Now there are other properties. You can get the predict values. You can get, final model you can get. So it will print the final model also based on those selections we did. You remember that? Max code identification, M-try maximization, max code maximization, all those things. If you do that, then you got the final model. Okay. So store max.
So one question. So why don't we just see both kappa and the accuracy for everything? Why just check only for one? We could do both together to avoid any problems, right?
Where is check for only one value? I mean, they are together. Remember that they belong to the same collection of outputs. So you have to look at both. Yes, you are right, and that's what I did.
You said that when the the values are something, you said when it is low. I forgot that. When do you see when kappa is? When do we actually have to see kappa?
When the data are imbalanced, kappa becomes very important. So it is imbalanced data. So you are using kappa also. I said, right?
So if it is a balanced data, you don't have to see kappa. You're trying to say that?
That is correct.
Okay.
Where if it is a balanced data, your accuracy is good enough for you. Okay. But accuracy can be misleading if it is imbalanced data, because one class may have 70% and its accuracy will be 78% or 80%, but that is not good enough, right? If I have 1,000 observation, 500 observation, and let's say 3 classes, 500 observation goes to one class, 200 observation goes to another class, 300 observation goes to another class. The 500 observation, it should achieve, 500 out of 1,000, right? It should achieve at least 50. Definitely. In fact, we are saying 500 out of 1,000 because it's a 3 class. What is 500 out of 1,000 for the 3 class? It is 0.5, but it is a 3 class problem. So what happens to the, you expect 0.3, 0.3, 0.3 to be equal, 0.33, 0.33, 0.33 to be equal. In that case, if you achieve 50%, it's great, right? In that class, but it's a 3 class problem, but the first one has 500 observations. So we expect at least minimum 500, 50%, which means more than that. We should get 60, 70%, and so on. Are you with me? Otherwise, it is not really good because it is not even achieving the random allocation. Am I making sense to you? Randomly, if I put first 500 randomly, randomly 50% I put, because 50% of the observations are the class 1. If I randomly put 500 of them all will fall into that, yes or no? Randomly we put it will be good. So it should be more than that. While other classes, 50% if I achieve, it's great. Do you agree with me? Okay, that's what the problem we are going through. So these are all the small details you have to be very careful. Huh? Now we want to finally maximize with respect to the tree. So three things we are maximizing. One is M-try, the other one is node size, the third one is finally we maximize how many trees we have to build. Everybody's good? That is what the optimization.
No, can you repeat that sentence?
No, first we selected, it's 3 parameters we want to optimize. Okay, one in this case we are optimizing number of variables to select because it depends on number of variables you select, and then number of observations you have per node, right? And then finally number of trees you build. So that is what I'm optimizing in the third point. Number of trees is optimized here. So I start with 250 trees, 50, 50, 50. I add until 550, and then 600, and then I add 200, 200, and then finally 1000. Because otherwise it will be a large number. It's good enough. Are you with me, everybody? Again, I'm doing the same thing. Okay, everybody. So node size max nodes is 7.
So can we say that kappa is somewhat like normalizing the data?
You mean what is called standardizing the data?
Yeah.
Okay, why
Is
did
it
you say
somewhat-
that? Why did you ask that question? In what context? Go ahead. You have some point here. Okay, go ahead. Why?
No, you were saying that only if the data is not normal, then only we do this kappa thing. Then only we look at it. So is it like some kind of normalizing the data and then we look at this kappa thing?
It's not normalizing the data. See, standardizing the data. Let's call it as a standardizing, or sometimes people say harmonizing. Standardizing is good. Okay, standardizing the variables. We would do that also sometimes. Okay, so that all variables will get the same range 0 to 1, right? If I take the mean variable minus mean divided by standard deviation, it will be usually between -3 and +3. Okay. That is standardizing the variable. That's also called z-score. You can use that to standardize all the variables so that they're all within some range. That is a different problem. This one, it's not normalizing. It is kappa is helping you to see in relation to its random assignment. See, random assignment, if you can do randomly 50%, then you have achieved more than significantly. For other classes, if you achieve 50% for other classes, it's great. But for a class which already has 50% of it, or even 70% observation, if you achieve 60%, it's not good enough. Are you with me now? Because this is what a case of imbalanced data. This is called imbalance categories. Okay, these dependent variable classes are imbalanced. That means they are not equal. If they are imbalanced, it is natural to even if you randomly assign, don't have to build any algorithm. If you randomly assign, first class will get 70% accuracy. If it is a 70% incidence rate, 70% accuracy, to randomly assign, it will get it. But 70%, it depends on what is its incidence rate. And such cases, kappa helps you to figure out whether it is a useful situation or not, useful prediction or not. Okay. Think about it, and we can go over a few times also. So finally, we do the model, and the number of folds is 5. Remember that one. I actually used as if it is 1 and 4, 7. So it is building it is printing that the model is M-try was held constant at 6. Yeah. You have a question, Rajan? Okay. It's a 5-fold again, right? Summary of sample sizes, 180, 180, 179, 177, 180. But the fivefold is doing that, right? That's split, right? Because it is not even number because the total sample was not divisible by 5. And here the accuracy turned out to be 72%, kappa is 0.56. Tuning parameter M try was held at constant at 6. Okay, tuning parameter was held at constant 6. And then the confusion matrix in that situation is this is what is happening now. This is the prediction. This is the actual. This is the prediction actual. Sometimes, confusion matrix, you have to be very careful, what you use where, this one. Okay. So it is about the test data. We don't have that much data in the test data. That's the problem. It so happens. Test data is not that many. That's why you get some of the few cases here. Okay. Also because the data are not distributed evenly. So we have finally some model. The model says that you have fixed certain M price, certain node value, node number of observations, and then certain number of trees. And given that we also have the importance variable importance here, the plots for the variable importance. So these are the variables, and these plots tell you, for example, for the class, because you remember there are 5 classes there, right? So we need, for each of the classes, we need what variable matters, right? So that's why it is here. See, num1 is actually a translation of num. Num1 is translation of num, okay, num1. And num1 is basically the, if you look at num1, it's basically the 0, 1 category. So it's already a dependent variable. So I shouldn't be using this num1 actually, okay? So that's why num1 is becoming very, very important. I shouldn't be using it, because it's just a translation of num. I should, subtract that one. So this was, it was not running initially, so I was running it. So I ran something that was running it. I completed something that was running it, but I will drop this one out of the modeling. Are you with me? It's an incorrect one. Num1 should not be used anymore because it is just capturing the dependent variable partially. But rest of the variables tells you. So to the left means it's negatively correlated. To the right means it's positively. And for example, in this case, let's say this variable. What is this variable? THALACH is very important for S2 category, but that is not very important for S1 category. Positively not doing it, okay? But it is also becoming important for H category, which is a normal part. Not important this one, for important S3 and S2. They are different levels of criticality of the art situation. So for everything, the variable importance prints out for every class. That's my point. So here is the situation, right? So if you are given a problem to solve, and this is a multinomial class, you can even do for binary class, very simple. How do we optimize the number of trees? Oftentimes, number of trees is a free-flowing number. Number of variables to select, number of observations. These are three critical. These are three critical parameters: number of observations per node, number of variables to select, and number of trees to build for the fast. These are three. So this is how you optimize it. I will go through this one more time. This optimization here, whatever I have done, because there is something it's not clear here. I need to get back to the notes there. What has happened? Why they selected it? Somebody's code this one. Okay, so I'll get back to you on this one next Saturday. But in the meantime, you can try this. You all have to go through this. What is called the hyperparameter optimization. If you are going to use random forest or even XGBoost, we'll come to the XGBoost also. We have hyperparameter optimization in XGBoost also. The big difference between random forest and XGBoost is that XGBoost, it's not only boosting, but it's also has regularization, which means the more the number of parameters you throw in, the model will predict better. But predict better for the training, but not for the testing. So how do you balance the number of parameters? Is the problem addressed by regularization. So we are going to talk, I introduced boosting today. I will introduce XGBoost on Saturday. Next Saturday, I'll introduce XGBoost. But in the XGBoost, we have two parts to it. One is, it is the boosted method. It will go reach the accuracy. Its purpose is to reach the accuracy, highest accuracy. Okay? But remember, there is a balance is always there. The bias variance trade-off. Okay? So it reduces the bias. It will give a smaller model, smaller forest. Because less number of parameters, it will have also reduced variance. Okay, bias is trying to reach the highest accuracy with the lower number of steps, which means it is supposed to go through lower number of parameters. So XGBoost, is an efficiency built on boosting, and we will do that also. So there also, XGBoost is done using trees approach. Again, it's a trees, okay? So but because it is trees, it is also applicable for both classification and regression. And we will go through XGBoost next time. The additional benefit of boosting in general, with especially XGBoost, is that boosting is to go in the direction of reduced error, right? But XGBoost also penalizes the number of parameters. So that is why the XGBoost is more trustworthy in the case of the testing data. Understood what I'm saying? It's more trustworthy because it is controlling for expansion of, there is a tendency to throw in more and more parameters. Algorithms have tendency to throw more parameters because in the training that is going to give you a great result. But unless you penalize it, it's not going to do well in the testing. And that is what XGBoost does. And we are going to see the XGBoost as a penalized boosting method in the next class. And we will do the same thing. This analysis we will do there too. How is everyone doing?
Okay, sir. Practical, can I take the next class half?
You want to take off your time?
No. Next class, can I take half of the practical?
You want to conduct the class?
No, half of the practical.
Oh, okay. No, you can do this. This is such an important part. We might want to redo this, either with a new data or the same. It's okay.
Yeah, we like to redo this, please.
It's okay. It's fine.
Yeah.
Or we can do one thing, redo this and then give them, another assignment also, let them repeat the same thing.
Yeah.
But it's such an
I'll ask them I will give another data set and make them do that.
Okay. That's also fine. But the point is, you have to understand what is this hyperparameters, how it's happening, what's going on, how do we reach the final answer. This is the well-trained people in machine learning. Machine learning, broadly speaking, two parts. One is the random forest and boosting method, XGBoost. The other one is neural network. Well, I shouldn't say that. 5 things are most important in machine learning. One is random forest. The other one is boosting. Third one is neural network. Fourth one is neural network, also what is called the average neural network. Okay, because you do multiple neural network and then take an average. Okay. Fourth one is SVM, support vector machine. We will teach that one also. And of course, final one, I will say final, it will be the first one, logistic regression and regular regression matters. Just because you do neural network, don't think that you can solve all problems using neural network. Sometimes neural network may not work out. It will
So
work.
is the deep learning a part?
Deep learning
So
is
is the
neural
deep learning
network.
a part of AI?
Deep learning is neural network applied for unstructured data. Let's do it. Let's say it that way. Yes, it is part of our course. Which means we will talk about predicting images, predicting text. Those are the two things only we'll do.
How about voice?
Voice also you can do, but there is no time.
Okay.
Video also you can do, there is no time. Okay, so we will do only these two. So regular regression, if you do it well, it will do great job, and the best part is you can explain to others. Regular logistic regression, if you do, it will do a great job. If you do well, it will do a great job. Sometimes it may not, but sometimes even neural network may not. That's why I'm saying 5 methods. Okay, if you want, you can write it down. Regular logistic classification, if you take it, regular logistic regression matters still. And then matters random forest. Third one is boosted random forest. Fourth one is SVM. Fifth one is average, the neural networks. Neural networks is, it's shown in the book, in a book by Max Kuhn, that average neural networks do good job, even for structured data. See, usually you have no choice other than to use SVM and neural networks and boosted regression trees for text data, for images. In fact, images we don't use even regression tree. The random forest and random forest and boosting we don't do, because there is so much application about neural network. With the images, people just rely on neural network. But there is an issue about neural network, which is only I kind of think about it. I'm not practitioner think about it in general. If you in neural network, you will throw in millions of parameters, because they have millions of data points. They can afford to do that. So, is that the only way to do? It is, research is still working on. Okay, so we will. I will introduce XGBoost next time, which is very powerful. So I said 5 things, but next time XGBoost I will introduce, because it penalizes the random forest. Penalized random forest, if you want to say. Okay, but random forest as it is doesn't have penalty. That was a problem. But in the beginning, it was doing great. In competition, it was winning. At that time, when only logistic regression was there. And then boosting came, boosting won. Still, XGBoost is a winner even today. Okay, in comparison to neural network. But most of the time, XGBoost is, as far as I know, it's just working only on structured data. What statisticians have, right? Structured data. But unstructured data like images and text, voice, all those things, it's still neural network works out better so far. Okay. Any other question? All right. I want to close this today a little early, because I want to stop it here. Is that okay, everybody?
Yeah, sir. I think it's good, because let them absorb all this and go through this example. By week, they will let them try this, and once they get the idea of it, once they work with me, the second half of the practical session next Saturday, they will get a better. They'll really get a hang of it. And also, you're going to be talking about XGBoost. So this should be in the, this should be the right base set for understanding that as well. So I think it's good.
Yeah, it is very important. There may be some additional notes I may send for this example. I just ran what the other people ran. There may be some little explanation somewhere there I need to give. I'll do that. Okay, in the meantime. before
You also shared those decision tree, random forest. There were a lot of PDFs previously shared, but I'm not getting it at my end for the references you had for decision tree and everything.
Yeah. References in one place. The one I sent today.
Some
Right?
snippets were there.
Huh?
Some snippets, part of presentation or something like that. Easy to understand kind of.
Yeah, I'm kind of improving some of these notes also, expanding some notes and so on. So that's why you may not have it. And so let's continue to keep these things in one place, continue to, I need to have a better process by which, whatever I edit, I don't have to post it, it's already there,
Yeah.
That is where I want to get, because, these things need some additional notes, additional research people are publishing, so. Okay.
Okay, sir.
All right. Thank you very much, everybody. Have a wonderful rest of the evening if you are in India, and rest of the day for Rajan. Thanks a lot. Is that good?
Yes, sir.
Yes, sir.
Rajan.
Thank you.
Thank you, sir.
Have a great week ahead, everyone. Take care. See you next Friday, Saturday.
Okay. All right.
Okay?
Yeah, bye.
Bye, guys. Bye, sir.
Bye.
Bye.